All right, Steve, the stage is yours.
Okay, another sound check. Everyone can hear me okay, I presume.
Yes, great.
So first of all, thank you for the invitation. I truly enjoy talking to people about something that's been very big part of my life because I lived through Hurricane Helene here in Asheville, North Carolina, as did my two co-authors, Bill Christie, who works with me here at the Southern Research Station of the Forest Service in Asheville, and Greg Dobson, who's across the street at University of North Carolina, Asheville. We've had a long-standing collaboration with. And the specific focus of this presentation is how we map something that's really unusual and a bit unexpected, as we'll see. The impacts of Hurricane Helene last September were truly spectacular, and it came a bit as a surprise. The wind impacts, record floods, record landslides. And so it's been a challenge over the last 8+ months to get a handle of it, on it, and to give managers, the responders who are still actively trying to respond to different aspects of the storm, the information they need in a timely manner. And so toward that end, I'm just going to come up with provide a quick summary of what happened, show how we've rapidly mapped impacts and talk about the limitations of it, and then talk about fire-related risks in particular. And I really love this new NOAA website. It gives anybody the opportunity to look at their county or their location and look at the history of hurricane tracks as best as they're known. And Asheville, North Carolina, here's where I'm centered. So I chose that county. And these are all of the tracks that we know of in 1,000 miles of Asheville since 1851. And the colors represent their intensity. So as you can see, most of the ones that are offshore are quite often still hurricane speed. Some green pass over the continental US, and most of them are blue. They're tropical depressionless, so the sustained wind speeds aren't that high. Helene is one of those more intense storms from the get-go. You can see it's been boldened here to be a thicker color, but it's in the green. It's a tropical storm, and that's from just south of Atlanta all the way up into Kentucky. And because this was so special, the number one question everybody's struggling with is, how exceptional is this? How likely is this to happen again? How do we plan for something like this? We zoom in and just look at the nearest 100 kilometers of hurricanes, we get a little more insight about how these prior tracks that we know something about and how they affected our area, or did not affect the area that much. And why that might be the case. So we know the storm was very intense. It came inland, but we've had other storms that intense. If you look on the right side, Hugo in 1989 was actually orange. It was a Category 2 storm when it came up, did a lot of damage in Charlotte, came up to the east of us. Hurricane Helene was to the west of us. That makes a huge difference because of the way the winds rotate around storms. And if you look at other storms that are west of us, some of them jump out. Zeta in 2020 went just north of Buncombe County, but I was living here then. I don't have any recollection of it. So it's not enough to just be an intense storm. This unnamed 1916 storm to the south of Buncombe County is very famous. That was our previous record flood year prior to Helene. Unnamed 1906. I looked information about that. I couldn't find anything about that. So there haven't been that many storms that have gone to the west of us that have been so intense in 174 years. One of the peculiar things that really jump out, I think, extreme rain. The extreme amount of rain, and it's not just the rain of the day of the event, but the predecessor rain. the rain that fell in the 2 days before. In fact, almost all the weather station data we have suggests that there was more rain that fell on September 25th and 26th than occurred on the day of the storm, September 27th. And it's a little bit unfair because the storm pretty much had passed through by the time you get to noon. But that's really important because all that rain made the soil very soupy and very saturated. So when the wind came, the trees were able to blow down very, very easily over large areas. The white line you see on this map is the Blue Ridge ecoregion. So think of that as the Blue Ridge Mountains, Southern Appalachians, outside of the Cumberland Plateau. In the upper left, it's the Blue Ridge Mountains. And most of the intense rainfall is in the pink and the white. That's on the eastern escarpment of these mountains. And that's important because when the winds come, they bring the rain, they hit the mountains, and you have a lot of orographic precipitation, especially in places like Mount Mitchell that had I don't remember how much it was. It's over on the right. What does it say? Mount Mitchell EcoNet 24 inches. And just to the east of it, the Busick station had 30 inches of rainfall over those 3 days. The wind speeds are also amazingly high, surprisingly high. Mount Mitchell had 106 mile per hour gust. To the southwest, Frying Pan Lookout Tower had 87 mile per hour gusts. So these same areas that had a lot of rain also had some pretty intense wind speeds, those higher elevations. What's amazing is a lot of our tree effects were not at higher elevation. They were down much lower. And you can see at 8 a.m., we had some pretty intense winds. As the storm moved to the northwest, those intense winds persisted in some places near the northern part of the North Carolina-Tennessee line. Impacts were also felt up in southwestern Virginia. So Helene was not surprising. In some ways, we get downbursts and we have trees blow down every time there's a tropical storm, year after year after year. We have flooding routinely every few years, not major flooding like this, but some flooding, and landslides are common. In fact, we had a massive landslide year just a few years ago when Hurricane Fred came through, killing a bunch of people just west of Asheville. What made it so surprising is the numbers of them and the magnitude of this. So how many landslides we have, how high the flood was, the sheer number of blown down trees, and the size of the gaps, the patches that formed. It's the sort of thing you normally see on the coastal plain, not in the mountains. The location of damage was a little bit of a surprise. It wasn't just on the more wind exposed sites, but there were downbursts, and so there was plenty of blowdown in the coves and the valleys. You'd think they'd be wind refugia, but they're not when Helene comes. A lot of uprooting. Almost all the trees are uprooted because of that combination of wind and rain. We don't have that many snap trees. Differential impacts by tree species are out there. Some species are a little more resilient. And we've had a lot of surprises, secondarily, with the fire behavior and some insights that have been gained that we did not anticipate before. Looking ahead, we don't quite know where we're going and what our assumptions are. So just to understand how extensive some of these patches are, this is Lynn Cove just north of Asheville before Helene, and that's the exact same area after. And you can see the poor homes here, homeowners are surrounded by all of these fallen trees. Used to look like that. Now it looks like this. And the reason it's a patch like that is because of topography. Everything in the upper left-hand side is a wind exposed, more southeast facing slope. And the intact forest in the lower right is a little bit wind protected facing northwest. So a lot happens suddenly. How do we map it? Well, we use satellite remote sensing for everything here at in the threat center at the research station. We routinely are mapping disturbances, and so this isn't our first rodeo for trying to map hurricanes in particular, but certainly at scale in the mountains. So we applied our technology, which is change in NDVI. We find that is a robust index that we understand well, and it works for a number of different disturbances. and we like integrated measures. So this is a change map we came out with in I think 10 days after the storm. So early mid-October, we had a clean refinement. There might have been a few clouds in the first versions. And the intensity is shown by this gradient from blue, which means there's no change from the year earlier. And this is October, right? So we're in the fall. No change. Yellow means there's a little bit. Red means there's a lot of change. It doesn't say it's damage. It says it's change in the NDVI, or the greenness of the vegetation. And you can see most of it's northeast of Asheville. The same essential pattern we see with other change detection imagery and indices, that most of the impacts northeast of Asheville. At 10 meters, we can see a lot of detail. So this is an oblique view looking north up Linville Creek, Linville River, just east of Asheville. It's one of our first wilderness areas, and it's probably the most fire-prone area in the mountains. It's been burned repeatedly. The fire return interval in places here is all but restored, and it's all from wildfire. There's prescribed fire around, and a huge amount of money has gone into restoration. So when you have a bunch of trees come down and a lot of fuel, you start to get a little concerned. So we know from field observations that a lot of these more stronger departures are indeed blown down trees, even the ones down here along the creek. These small little patches here are legitimate patches through this landscape. Some of that over there in the upper left is a little more suspicious. And it's suspicious for this reason. Fall means the leaves are fragile. So normally by mid-October, we're starting to see a lot of senescence and leaf abscission, especially in these higher elevations. So we did a little validation just to try to understand how much this departure relates to actual damage and how much of it relates to possibly leaf stripping. And we have worldview imagery that gave us an understanding of this. We don't know for sure what's going up here in the top. They're fuzzy impacts. It's probably leaf stripping. There could be some fine branches, but I'm calling it fuzzy because it looks fuzzy at 30 centimeters. Sometimes you can see actual blown down trees. That was obvious. And in a lot of places, the forest looks absolutely fine. So generated 500 random points, 375 of them fell on forest within this worldview 30-centimeter resolution tile from October, and just called it classified. And those are the three colors you see on the graph. The blue is blowdown for sure. You can see the fallen trees. The gray is kind of fuzzy. Not sure what that is, but probably stripping. And the green means it's visible change. Well, what's remarkable as you go left to right on this graph, it's more and more NDVI departure toward the left. And what's amazing is there's plenty of no visible change, hunky-dory green canopy that has quite a bit of departure. Not much, not much overall, but there's plenty of it that is more than 10. And that's because it's the time of year. It's senescing. Maybe there's a little bit of leaf stripping. It appeared good to my eye. The important thing is in the blue. This is where we have high confidence of blowdown. And when you get to about -20 or so, you're basically, and below, you're getting more confidence that you have blowdown. Half the time, at least, you've got blowdown. So there's a lot of ambiguity in this map, this October product. That's the take-home message. Why is that? Well, and where is that a problem? That's been a challenge for us. So we know that leaf stripping is a real phenomenon, and it's especially problematic at higher elevation. So down here in the lower left, this is a phenology curve. So it gets greener as you progress into spring. It reaches its summer max on the black line that goes down. Well, the growing season is shorter, both in spring and fall, at higher elevations. And so by the time Helene hit on September 27th, we already were well into fall senescence in these higher elevations above 4,800 feet. Those leaves were easily stripped off. Some leaves up there, like beech leaves, they'll stay there forever through a biological mechanism through a better part of the winter normally, but beech aren't the predominant tree up there. And so we have a lot of departure that's probably just leaf stripping on those upper elevation sites. Lower elevation sites like tulip poplar, we have a lot of leaf stripping up here. These areas lost their leaves because tulip poplars just senesce early. It's what they do. It's a biological thing. No structural damage, just leaf stripping. So it's for us, if we're trying to map structural damage, that's a false positive. And we don't know exactly where the tulip poplar are. So that's a bit of a challenge. Sometimes if you have massive blowdown, like in the upper right, yeah, of course there's leaf stripping. The leaves are in Tennessee. The whole trees are gone. It doesn't even matter at that point. So those aren't a problem, and they can be very strong departure. In the conifer areas, interestingly, it doesn't really matter because those spruce trees, this is Roan Mountain in the lower right on the Tennessee line, a lot of fir, not balsam fir, Fraser fir blowdown up there. And the damage was pretty well mapped from the beginning. So this is a common problem even in spring with tornadoes. In the eastern deciduous forest, leaf stripping complicates our ability to assess damage. So we have 3 assessments. This is a timeline of what we can see, the seasonal sensitivity of our technology to pick up what we want to see. We want to know deciduous damage and conifer damage. Well, you want to do it, you want to know right away too. So we have a rapid assessment process that we know has some false positives from leaf stripping here in October. But we're also picking up canopy impacts. It's kind of blurry. Where we have conifer, we're picking it up pretty good because, you know, we can pick up conifer impacts pretty much year round. And we've done this winter assessment already in March to capture better the conifer impacts, but also the landslide impacts and scouring stream impacts. That doesn't tell us much about the trees. We already knew the conifers. But this summer assessment that we're on the verge of having here, once the clouds go away in the next few months, is going to be a better, clear view of what actually happened within the deciduous forest, because that leaf stripping phenomenon, those false positives, have just gone away because now the leaves are already out again. This is proof of that phenomenon and the value of waiting 9 months. This is the October change map on the left for the Asheville watershed. This is a real blowdown here, but this is kind of ambiguous here on the east side. The winds are coming in from the east. Pretty much all of it went away with this March assessment in the middle. You can see the geomorphology, the scoured streams really well. A little bit of echo here from where that blowdown was. But this has gone away. Most everything's gone away. It's a very clean product because we're only seeing conifer impacts and only seeing geomorphological impacts to the streams and landslides. If you look right now, we still have a little bit of cloud here on this current product, but that landslide's come back because the leaves came out when they could. If they were dead trees or fallen trees, they did not come back. And all this in the lower right is missing. Why? Because it was leaf stripping. And we know from this 2-inch resolution imagery that we have for Buncombe County exactly what it looks like in mid-October. This is the divide right here, comes down. So there's the divide. So that box is this whole background image. And you can see that the trees don't look fallen. There's a few fallen trees up here. You can see through the gap, the canopy gap. For the most part, it's just leaf stripped. We expected that to go away and it did. Meanwhile, up here in this area, it's a legitimate blowdown. All that stream is scoured because the landslides are up there. This is real. And it, as you saw, it has now come back as an anomaly, really strong. And it gives us confidence in the value of waiting. This is the reason, by the way, that Asheville's water, one of the reasons why Asheville's water supply was so cloudy for a couple months. So we have good high resolution world view in some of these areas. This is Armstrong Creek, northwest of Marion. And you can see all the blowdown here on Pisgah National Forest land. You can see the blowdown root wads. Some areas their forest is relatively intact. So this is what the October change looked like. Lots of purple, lots of extreme change. This is what it looks like now in the summer product. And you can see that we're capturing with some warm colors, yellow to red to purple, the damage now. but the threshold is different. And you might say, well, is that a problem? And the answer is no, because this is what it looks like right now. On the right, it's greened up partially. A lot of these trees, they blew down, but they still have vegetation. The forest is not completely dead. It's not been burned to a crisp. It's still there in part. And so that recovery, that spring recovery, changes the threshold we have to use to define what constitutes damage. So change in fire risk. How's my time? Am I on time? Hopefully. There's three aspects to this that we have to think through. And we're talking about disturbance interactions here, how Hurricane Helene affected some aspect of fire. And there's three important things to think about with regard to fire: the way we respond to fires and wildfires, and how Helene might have affected that, changes in actual fire behavior, and changes in the outcome and the effects. Wildfire response, probably more than anything else, is been on the minds of the responders that we've had out in the woods over the last winter, spring fire season, because they're dealing with all this stuff freshly after it happened. And we have a lot of insight as to the challenges they had just because of their collective experience. Fallen trees, when they cross a fire line, a pre-existing road, somewhere you might want to put a bulldozer to stop the spread of a fire, even a trail in a recreational area, creates a lot of complications because you need to take time to cut those trees out to make sure it's a secure line. And you have debris. That debris gets piled up on either side of that line, and it can create some member hazards and make it harder to establish a effective and secure fire line. Also, of course, creates safety issues when you have some fuel around your fire line. So the wildfire response has been more complex. Wildfire behavior, fire behavior, if it's a prescribed fire, there's plenty of reports of local increased intensity from the suspended fuels, all the leaves that are just hanging up from blown down canopies, the fine wood in the canopy. That creates a lot more ember spotting, and we have plenty of reports of that. Over the long term, we're worried about smoldering in these logs once they start to decay, creating a long-term smoldering hazard for the region. Because in other places in the coastal plain where hurricanes have come through, that smoldering hazard persists for decades and decades and decades after the storm. When we have fire after blowdown, we have a lot of debris that decay, the decayed logs, once they've decayed, and just set right next to a tree you might want to keep and smolder and create fire cavities like this on the lower left. Fine for wildlife, but it does shorten the life of the tree by introducing decay. It can have fire after heavy blowdown might have some complex successional effects. And the biggest thing we're worried about are non-native invasive species. They can take advantage of all these upturned root tip mounds, all this bare mineral soil. It's hard for us to even monitor because you can't get through those thickets. Wonderful seed beds because of the uprooting. And in the intersection with fire, that creates even more opportunities for non-native plant establishment in those most disturbed sites. So this North Fork fire we had in January, the perimeter is shown here, and you can see how quite often these perimeters are cutting through areas of higher severity shown by the warmer colors on the map. This is a dozer line here, bulldozer line they established to protect these structures on the upper left, and it had to go through some rather severely blow down areas. This is the city of Asheville. Here's the city forester, and they cut this trail open, but now look at all the debris they have to deal with. And this is in a decent sized park in West Asheville, very, very close to homes. Major fire hazard. Running back to Linville Gorge, a lovely place that I like to visit. This is what the fire line, a major fire line, potential fire line looks like. There's a lot of debris there that needs to be managed somehow. And this is, again, one of the most fire-prone wilderness areas we have. So one of the surprises that we came out with that kind of emerged from discussion and observations is we weren't quite sure where we're headed in coming years. So much of our fire spread is dependent on leaf litter of the canopy. Well, we have areas where there's massive loss of canopy. And if those trees aren't with us anymore, they're not going to produce leaves. And those leaves, being critical for fire spread in the past, are not going to be there anymore. So what's going to take their place? Well, eventually maybe the brush, the secondary succession. And that dynamic is captured by two of these lines. The line here of leaf litter falls from pre-Helene conditions down maybe year to year to year, where it's less, and gradually recovers. The brush, the regeneration, the non-woody stuff that might carry fire increases gradually, but it takes a little bit of time for that. One thing that everybody talks about who's on the fire line this past spring are these suspended fuels. So oak trees in particular, white oak, red oak, when they fall over, those leaves hang. The trees got uprooted before they realized it was fall because oaks senesce very late relative to the mesic species like maple at this elevation here, 2,000, 3,000 feet. And so those leaves never had an opportunity to start their normal fall process of senescence. And there's in a lot of places they're still there now. Well, those are fire ladders of concern on the fire line, but also in the interior, creates embers and hazardous conditions. That's represented by this line right here, this red line. It goes up. It's just now we have it, and it's going to go away, and it's not going to come back. That changes the fire hazard. So, I mean, if you add all these, the last part are the logs. Well, you think all these large logs might become a fire hazard. Well, someday they will, but not until they started to decay. Right now, some people are reporting on the fire lines that the logs are fences, they're barriers for fire spread when they're touching the ground because the fire burns up to them, the bark's intact, the wood's still green, it's not burning. It takes an ember to jump over the log. And so the logs may actually be having a negative effect on fire spread for now. That will change. But for now, that's represented by this gray dash line. So if you add all those up just in a crude conceptual sense, this is all hypothetical, of course, you get a curve kind of like this red line on the left. An increased hazard now, maybe a little bit less in the years that come if it's a complete blowdown area, and then it will rise up again. Now, a lot of areas like the area behind, in the photograph behind, there's partial canopy loss, so you're not going to lose all your leaves. So much of that is dependent on that leaf litter. And so there, it might just generally, it might stabilize or go up a little bit without having dipped down in the next few years. These are speculations, but they're questions that we've been asking, and they're questions that we can't get answers to with our existing fire behavior model. I don't expect anybody to dwell on this too much, but when we try to understand fire risk, we think about a classic way that's developed over the last decades has been just to think through scenarios, fire spread scenarios. You have areas of ignition, historical, you can apply those to a map, fire spreads based on the topography, the fuel, the wind conditions, the canopy conditions. And you end up with some sort of fire spread outcome. And if it's nuanced properly, it depends on the response system you have. Some places are easier to get to than others. And then you have an impact question. If you want to know what the impacts of all this fire in a landscape might be to structures, you got to think through all that. There's a lot of complexity to it. Well, what happens with Helene is everything suddenly is outdated. Everything is obsolete to some degree in places where there were big Helene impacts. Helene altered fuels in a huge way. How did it? You know, there were questions like, what's the crosswalk for fuel? What do we just give everything a slash fuel model? It's hard to know what to do because we haven't seen a storm like this at this scale. We also have canopy change. Canopy reduces wind speed. It increases the sunlight in the spring and fall fire season. is an important regulator of fire behavior. Once it normally greens up in the summer, it shuts down that fall, it shuts down the spring fire season very, very abruptly historically. Well, if the canopy's gone, is that going to be the case? Is the sun going to be able to bake these areas in June and July when the fire potential is so extraordinary? The answer is maybe. Depends on the weather. So from all this complexity, what we did is just kind of focus on two things: the Helene impacts to fuels and canopy in a very general sense, and topography, which has a functional role here. Topography affects the fuels that are there. It affects the wind, fuel, moisture. It's kind of a critical player in all these scenario models. We looked at land fire fuels. We decided not to come up with a sense. I use those to understand how these homes all through our landscape might be at risk. So we have damage maps from October. That's in the upper right. That's the severity. The colors represent the severity. And we have topography represented here as relative site dryness, just moisture, site moisture. So the browner colors are drier south-facing slopes, basically. And this is a standard moisture index. The blue areas are relatively mesic, moist, north-facing coves, not ridgelines. And we smoothed the Helene damage. That's down here in the lower right. And then we just put the two together. All the black dots are homes to come up with a very, very general, simple sense of where there might be homes at risk. And there's a lot of them in this region. 600,000 homes in these 16 affected counties. Some of those had a lot of Helene damage. So the amount of Helene damage is represented by the y-axis here. So if there's a lot, that's in the upper tier. If there's none at all, it's in the lower tier. But it's all in the context of that background fire hazard. And for us, in this scenario, it's just site moisture. So the worst case scenario, you could argue, are those areas that have a background high fire hazard because they're on dry sites, and there's a lot of Helene blowdown. And guess what? That's 3,000 homes, 3,063 homes, which is 0.5% of the homes in this area. We also have lower slope sites, valley bottoms that had some Helene blowdown, and they're represented here. That's 0.8% of this landscape, almost 5,000 homes. It's a simple approach to get that. When you combine these 9 colors into a map, you get something like this for 2 places. It helps you see which homes may be at relatively high and low risk without the burden of some of this more complex modeling that had a lot of, it can't deal well with novelty. You have novel fuels. And we have a lot of data uncertainty, as I talked about earlier, with regard to the leaf stripping and the implications of damage as we're trying to assess it for a fuel model change. It's a very simple approach. So all of our data are available here on this website, our project website, highforum.org. If you go to severe weather, you can see examples over the last few years. Under severe weather, you can see our page for Hurricane Helene. And in the lower bottom, there's a PDF that has links to the maps you can explore in ArcGIS Online or download for your personal GIS use. We do not have yet a summer impact map, but that should be coming pretty soon. And with that, I guess, open for questions.
Thank you, Steve. That was great. And the figure you have about going to 2030 just constantly reminds us the risk is not just for a year or for one season. It's really a ongoing issue with the fire in the area was affected by Helene. So let's see if there's any questions from the audience. But before I do that, we're gonna stop recording so people can feel free to ask questions for the discussion.